wanted to do this example to reinforce the concept of work and energy theorem. T1 plus the work done from 1 to 2 is equal to T2. And this problem does it pretty well, and it's not necessarily intuitive on how to handle the displacement. So let's take a look at it. We got a mass B, just a block or something, moving to the right with an initial velocity of 5 meters per second. It's 2 meters away from like a plunger that has a spring constant of 200 newtons per meter, and then that spring plus the frictional force, because we have a coefficient of friction, is going to slow it down, and then it's going to make it some delta x. And they want to know how far that delta x is. What is a delta x? They also give us the mass. We're dealing with friction, so I'm going to go ahead and say let's sum the forces in the y direction to get that frictional force from the normal force. That'll give us an acceleration in the y direction of 0. We just have the normal force. Let's draw that free body diagram. Normal force up and mg down. So we just have normal force minus mg is equal to 0, or in this case they are equal. Alright, the force of friction. Force of friction, there we go, is equal to mu k times the normal force. So we got mu k times mg, and we can calculate that right away if we want to. 19.62 newtons. Alright, what about our spring force? Let's just take a look at that for a second. How much spring force is getting exerted? Well, our spring force is pushing to the left. We'll give it a sign in a little bit, but it's a kx, right? And we know k is 200, and we're just literally looking for that displacement until it stops. So it's going to be x. Alright, we're going to use T1 plus the work done from 1 to 2 is equal to our new kinetic energy. But first, let's figure out what these work factors are. Well, we got some work done by that spring force, and it's in the opposite direction of motion. It's going to be, or sorry, the opposite direction of displacement, so it's going to be a negative. And we're going to integrate all the way from its displacement 0 to x. We'll call that 0, and we'll call that x. The force we found out was equal to 200 x, and it's got to be integrated with respect to x. So this gives us a minus 100 x squared. Alright, we got to hold on to that. What about the work done by the force of friction? Well, it's also in the opposite direction of our displacement, until we're only concerned about when it comes to a stop. So the whole time it's in the opposite direction of displacement and going to the left. We have a minus sign then, and we've got the force of friction dotted into the displacement. Or in this case, we can just do delta R, because remember I taught you friction's always in the opposite direction of displacement. We really just need to know the force and the displacement itself. Now, what is this? What is the displacement? Let's look at this picture again. It's starting here and it's ending here, so we have to include this x along with the 2 meters. So our delta R in this case is equal to 2 plus x. So we found out that the frictional force was a negative 19.62. And for our delta R, we'll put in a 2 plus x. Now you may not know what to do here. Well, we have a function x squared and a function of x. Let's put those all into the work-energy theorem and see what happens. Alright, well, we do have some initial kinetic energy, and we found out we had a negative 100x squared and a negative 19.62 times 2 plus x. And it came to rest, so we can say this 1/2 mv squared term goes away. But I usually write it anyways. Now we have a quadratic equation in x. Quadratic in x. So we know the initial velocity, we know the mass, we have everything except for the coefficient. So we have ax squared plus bx plus c is equal to 0, and y'all know how to solve that. And we get an x equal to 0.688 meters. Alright, I just saw that one and I thought it would be pretty valid to show, because this was not necessarily as intuitive as you might think, but if you follow the steps, the work energy, and then look at what that work was for each one, and then put it back in, you might see the light. Just keep practicing.